Very good. All right. Hi. So in this video, we're going to take a look at an example of running through the whole four-step process of a one-prop Z test. So we have a hypothetical population parameter that we have a claim about, and we'll collect a sample of data and see if that sample gives us evidence to reject that original hypothetical claim, or if it doesn't give us enough evidence to reject that hypothetical claim. So let me see if I can share this other example here. All right. There you go. So in this example, let's say that a video game strategy guide claims that a certain enemy is going to drop a certain item 25% of the time, determined by a random number generator. So every time that enemy is defeated, it's going to generate a random number, and it should be set up where 25% of the time you'll get that item, which would leave 75% of the time you wouldn't get that item. So let's say that a player wishes to test that claim to tell if there's any evidence that the true drop rate differs from that 0.25 or 25% rate. So the player defeats the enemy 80 times, and out of those attempts, the item is dropped 16 out of those 80 times. So the question here is there statistical evidence that the true proportion of times that this enemy would drop that item is different from 0.25? And we're going to run an appropriate significance test at the alpha 0.05 level to determine if we have enough evidence against that claim. Now, 16 out of 80, yeah, that's 20%. So we did get a different rate, but is that difference just maybe due to random sampling variation, or is that evidence that the original hypothetical claim was incorrect? So we'll take a look at how to put together a full and complete response in that process. So in step one, we are going to state. Step one is the state step. So in that step, what you do is you explain your parameter of interest in context, and you define a null and an alternate hypothesis. So in this case, P is equal to the true proportion of times the item would be dropped. There's a couple of good little details here to really show that this is about the population and not just about our sample. Number one, make sure you use the symbol P and not P hat. Never use P hat here. Also, I like to use the word true or the phrase true proportion because that implies it's about the population. And make sure you don't explain this about how many were dropped. It's about how many would be dropped. So this is about the whole population. Our null hypothesis is going to be that the proportion equals the hypothetical claim that came from the strategy guide of P equals 0.25. And the alternate hypothesis will be what we're looking for evidence to support that it's somehow different from 0.25. So if you read through the problem, you have to look for, is there an indication of a direction, greater than, less than, and if not, then it would just be not equal to. And our problem said, is there evidence that it differs? And that doesn't give a specific direction, so we'll just say our alternate is that P is not equal to 0.25. So that's step one. Explain your parameter in context, define a null hypothesis, alternate hypothesis. Step two is the plan step. And in that step, you will explain the type of test you're going to run and show that all your conditions are met. So we will, we don't have to do that. That's for more confidence interval. So no, that's not true. We will run, got my mix up a little bit. We will run a one prop Z test at the alpha equals 0.05 level if conditions are met. Well, there's three conditions that we'll need to check in order for this one prop Z test to be valid. Number one is we need a random sample. And so the outcomes are randomly determined. And in the problem, it's stated that a random number generator is used to determine whether that item is dropped or not. So we have a random sample or a random outcome. Second thing we need is to check that n times p0 is at least 10, and n times 1 minus p0 is at least 10. Our sample size was 80. There were 80 attempts. P0 from the null hypothesis is 0.25, so we're going to use 0.25 there. It has to be at least 10. And so we would expect at least, or we would expect 20 successes. That's at least 10. So that condition's met. Then 80 times 1 minus p would be times 0.75, and that would be the other 60 would be fails, or where the item would not drop, and that's at least 10, so that's met. The third condition would be that if we're sampling without replacement from the population, we would need to make sure that the population is at least 10 times our sample size. But in this case, our population is theoretically infinite, so we don't really have to check this one. But there wouldn't be anything wrong about throwing that in there as long as you explain that we have an infinite population in this case. In step 3 is where you calculate. And there are two things that you have to calculate in this step. You have to calculate your test statistic or z-score. You have to calculate your p-value from that test statistic. So our formula for the test statistic in a z-test is that z equals p hat minus p0 over the square root of p0 times 1 minus p0 over n. Remember, we're using p0 and not p hat because we're assuming that we know the true parameter is 0.25. P hat in this case was 16 out of 80, that's 0.2, minus p0, 0.25, over the square root of 0.25 times 0.75 over 80. And so we end up with a z-score of negative 1.03 if you run that through on a calculator. So there's your test statistic. To get the p-value, we need to look in the normal curve and find the area of the tails. And because we have a not equal to in the alternate hypothesis, we're going to check both tails. We have a two-tailed test. So our z-score that we got was here on the left, negative 1.03. So we need to find that area. But we also have to consider the right side of the tail, 1.03 on the other side. So if we calculate that area of one of those tails, we'll need to double that. Let's see what we get there. So one way to do that, if you have an Inspire, you can use normal CDF, menu 652. Lower bound would be negative infinity, upper bound negative 1.03, and you'll leave the mean and standard deviation as 0 and 1, and we'll end up with 0.15. Due to symmetry, the other tail will be 0.15 as well. So the p-value is 0.30. So there's the two things that you need in this step is your z-score or test statistic, and you need your p-value. Let me show you how to do that on the Inspire. There's another way. Let me see if I can share that window or bring that window up. There we go. All right, so if you open up a calculator page, and where's my keypad? There it is. So what you'll need to do there is, that's not the one I wanted. There we go. Okay, so if you go to, we've seen menu 652, normal CDF. If you go negative infinity to negative 1.03, leave the mean and standard deviation as 0 and 1, that gives you the area of one tail. So if we just take that and double it, there's your p-value, 0.30. Now there is a way to kind of go through this process more quickly on the Inspire. using the z-test function. So in a calculator page, go to Menu, 6 for Statistics, down here 7 for Stat Tests, and that'll bring up all our stat tests that we have, and one prop z-test is number 5. So Menu 6, 7, 5 will bring it to your one prop z-test. P0, that's asking for the proportion from the null hypothesis, so 0.25. The number of successes in the sample, there were 16. The sample size, there were 80 attempts. And then your alternate hypothesis, you can click that or hit the right arrow. Just make sure that matches up with your alternate. So we had not equal to in the alternate, so we're going to leave that as prop not equal to P0. You'll hit OK. And there's our test statistic, negative 1.03, and our p-value 0.30. The reason why our p-value here is just slightly different is because I used a rounded test statistic when I use normal CDF. So this is a little bit more exact. In step 3, you don't have to show any work. If you just show z equals this, p-value equals this, then you're fine. That's all you really need to show as a minimum. All right, well, the last thing that we'll do is use that p-value in step 4 is to interpret or to make our conclusion. Take a look at our p-value. We'll compare that to our alpha level of 0.05 from the beginning. And because that is greater than 0.05, we do not have evidence to reject the null. We will fail to reject the null hypothesis. And make sure you also give the reason. And that reason is that since p is greater than 0.05, that's our reason, we fail to reject the null hypothesis. Make sure you put some context in here too. So this very last sentence is important. There is not strong evidence that the proportion of item drops differs from 0.25. So this right here is a full response of conducting a one prop z test. We started out with step 1. We stated our parameter in context. P was the true proportion of times that item would be dropped. Our null hypothesis was that P equals 0.25. That was our hypothesized claim. Alternate is that P is not equal to 0.25 because we just wanted evidence that it differed, but didn't care if it differed above or below. Step 2 is the plan step. So we said we would run a one prop z test at the alpha 0.05 level. 3 conditions were met. We had our random outcomes or random sample. The number of successes or fails expected were both at least 10. And our population was infinite, so it was more than 10 times our sample size of 80. In step 3, we calculated using the z-score formula and got a z-score or test statistic of negative 1.03. And then used that to find our p-value. Because it was a 2-sided test, we found the area of both those tails and added them together and got 0.30. Then in step 4, we used that p-value, compared it to our alpha level of 0.05. Since our p-value was greater than our significance level of 0.05, we failed to reject the null hypothesis. We did not have strong evidence that the true proportion of item drops differed significantly from 0.25.